In this session, let us see induction machine. If I have only one coil in the rotor, okay, how it is going to behave, how torque production will be. At the end of this discussion, you will understand two things. Basically, my way of dealing machines will be altogether different, okay, not from maybe your standard or reference books or your faculty, nothing like that, okay. Ours will be different. Now, at the end of this discussion, you will understand about reactive power a bit differently, okay. In transformer, we understood about reactive power. And in transformer only I repeated again reactive power, and in synchronous I repeated again reactive power. But now in induction you will understand about reactive power altogether differently, okay. Then you will become comfortable in the reactive power, okay. And second thing is about oscillational torques, okay. About oscillational torques, how it will be developed, what is meant by oscillation torques, and because of oscillational torques what are the disadvantages, you will understand today, okay. See, let me think of my stator, and in my stator, as usual, conductors will be there, A, B, C. These are connected with the sources, okay. And after that, let me think of the rotor. In this rotor, let me have only one conductor or one slot per pole. In the sense, means ABC is going to produce two poles from the stator side. As we discussed previously also, about the stator we don't discuss in induction. Only from the stator rotating magnetic field will come. From the rotating magnetic field we are going to continue analyzing rotor, okay. So this is going to be S pole of the stator. For example, it is rotating in this direction with synchronous speed of omega s. Okay, now if it is rotating in this direction, in this, maybe this is going to be conductor X dash, okay. So this will be let me think of short circuited ring, and this is short circuited like this, and this is going to be the shaft, okay. So for example, this is going to be conductor X, this is going to be conductor X dash, okay. Means that these two conductors, for example, this is conductor X, this is conductor X dash, these two are going to be short circuited at both the ends, Now, how the analysis will be, let us see. Okay, as of now, here induced voltage, NS poles are there, so induced voltage will be 0, and after 90 degrees induced voltage is going to be positive max, okay. For example, let me think of N pole, S pole, as of now is here, N pole is here, S pole is here, and it is rotating in this direction with synchronous speed, okay. Means only positions has been changed, that's it. Now, which type of induced voltages will be there in the rotor? For example, this is going to be N to S, stator flux, and my poles are rotating in this direction. Means that my conductor is rotating in opposite direction with respect to conductor, okay. So with respect to field, my conductor is going to rotate in this direction. So pole is here, this motion of conductor is in this direction, so induced voltage is going to be cross here. Induced voltage is going to be dot here. So induced voltage is going to be cross here. Induced voltage is going to be dot here. So induced voltage is in this direction, means entering into, and induced voltage is coming out. So immediately currents will flow or not? Yes. Okay. So because it is short circuited by its own, so currents will flow. Because of those currents, immediately whenever you have electrical current, automatically associated magnetic field should be there, okay. So for example, for time being, already we know that rotor resistance should be there. Without rotor resistance, induction motor will not work, okay. So let me consider rotor resistance is existing, but rotor reactance is 0 for time being. Under that conditions, only resistance is there, reactance is not there. So induced voltages are maximum, currents are going to be maximum, okay. So the currents are also going to be cross dot, Okay, so if it is cross dot currents, because like as I told you previously also, around this some conductors will be there because of net resultant, my net resultant MMF will be aligned with the phase axis in which maximum currents flow. So this is going to be cross current, this is going to be dot current. So this is going to be N pole of the rotor, S pole of the rotor. Okay, so because cross current, dot current, it is in this direction, so flux should be in this direction. You have to sit in the air gap as usual. If you sit in the air gap, flux is coming out. This is N pole. Now N repulsion will be there, S attraction will be there, S repulsion will be there, N attraction will be there. So torque will be developed in the same direction. Okay, so my RMF is rotating in this direction, so torque also is going to be developed in the same direction. Now, for example, I strongly hold at the rotor not to rotate. Under that condition, twisting movement will be there. Now, if I release the rotor, it will be accelerated in the same direction of RMF. Okay, so if it is released and if it is rotating in the same direction, already from previous discussion we know that. Okay, means my rotor will not be able to attain the synchronous speed. At less than synchronous speed, it will rotate. Now, for example, it is rotating with synchronous speed. It cannot reach synchronous speed, but it can reach nearer to synchronous speed. Now, for example, it is rotating with 1000 RPM. It is rotating with 990 RPM, and you are sitting on the conductor. If you sit on the conductor and if you observe the air gap, this is rotating with 1000, this is rotating with 990. If you observe the air gap, means if I sit in the conductor and if I observe the air gap, my stator poles will be passing through me with 10 RPM. Okay, so if I sit here, pass through me at 10 RPM. Okay, so it is rotating with respect to stator at 1000 RPM and rotor is already rotating at 990 RPM. If I sit on the rotor conductor, my stator conductor pass through me with 10 RPM. Okay, so if I sit here and observe the flux density, as of now flux density is going to be maximum because it is directly under the one pole center, and after that 0, after that negative maximum, because if it is here, you are sitting on the conductor, if pole is here, induced voltage is going to be maximum because flux density is maximum. When it is here, induced voltage here will be 0, induced voltage in X will be 0. When it is here, when N pole is here, induced voltage will be negative maximum, like that. So let me draw flux density. So this is going to be flux density which is happening in X. Okay, so what about the induced voltage? For example, induced voltage equal to BLV, sin theta and all will be there, not required, forget about it. Constant, and some people may think that V is voltage. It is not, it is velocity, and this is length of the conductor. So directly I can say flux density. Okay, so means flux density influenced by conductor X. Conductor X is sinusoid, and what is the here? Omega t, is it omega s into t or omega r into t or omega s minus omega r? Because stator MMF is rotating with 1000, rotor is rotating with 990. So if you are sitting on the rotor, my conductors will get 10 RPM. So omega s minus omega r. Okay, one more thing we can add, small thing. Now what is slip? Equal to omega s minus omega r by omega s. So omega s minus omega r is going to be s omega s, or we can say s omega s into t. Anything is fine. Now let us think of induced voltage. Induced voltage in conductor X. Induced voltage also should be aligned. Same. Now let us think of current flowing through X. Conductor currents. Okay. So if you think of conductor currents, see here, in this analysis, I considered rotor resistance, but I did not consider rotor reactance. Okay, so means reactance is not there, so voltage and current should be in line. So my current should be aligned with it. Now let us think of torque developed. Torque developed in X conductor. So what is torque developed? Torque developed equal to BIL. Okay, so length of the conductor, remove it, B into I is going to be torque developed, so torque developed is directly proportional to BI. Okay, now flux density and current will produce the torque. So if I think of torque developed because of X, sinusoid multiplied by sinusoid is going to be 0 multiplied by 0, 0, positive max, multiplied by positive max, and again 0. Negative multiplied by negative is again positive max, positive side only. So it's going to be like this. So torque developed is going to be average torque is positive. The average torque is positive. Okay. Now let us see what will happen because of this pulsating torque. Pulsating torque. Okay. Let me tell you one small example here. For example, let us think of this particular kind of induction motor is used for the traction purpose. Okay. So for example, this is the railway track. Upon that, let me keep my rotor. Okay, so means my torque developed is pulsational. At one time torque developed is maximum, at another time torque developed is 0. Of course, the average torque will be there. So my track will be there. Upon that, my wheel, that wheel will be connected to induction motor. For example, that induction motor is having only one coil short circuited, one conductor, another conductor short circuited. Okay. Then what will happen? Like this is the wheel. My wheel will get the positive maximum torque, and after that torque will be 0. After that positive maximum, after that 0, after that maximum 0. So because of this torque variation, though my train is operating at 40 kmph, for example. Okay. Now we may not observe that. As human beings, but my material has to. Okay, so because of the torque variation, my torque will be, this is the track, my torque will be more maximum and torque will be 0, after that maximum, after that 0. So wear and tear across these two will be more. Okay, so my material will be wear and tear will be more. Wear and tear in the sense, maybe within 2-3 years itself, you may have to change the track because of my pulsational torque. For example, in the rotor, let me consider, means resistance is also there in the rotor. Resistance should be there. Okay. And let me consider reactance is also existed. For example, let me consider rotor resistance is non-zero and rotor reactance is also non-zero. Reactance is also, let me consider. Okay. Now, for example, let me think of flux density as usual. Flux density in conductor X is going to be sinusoid with S omega S into T. Okay. If flux density is like this, what about the induced voltage? Induced voltage is Ex. Okay. That induced voltage is directly proportional to flux density. So my induced voltage is this. Okay. Now if you think of current, the moment you have resistance and also reactance, my current should lag behind voltage by tan inverse of X by R or not? Yes. So my current is going to lag behind. So for example, let me think of conductor current Ix should lag behind. For example, it is lagging behind. Okay. Now let me think of torque developed in X. Okay, so means what is torque developed? Directly proportional to Bi, as we have seen just now. Okay, flux density multiplied by current. Now flux density is black, current is blue. So positive multiplied by negative is going to be negative. Positive multiplied by positive is positive. Positive multiplied by negative is negative. So from here it is going to be like this. Okay, in this also average torque is going to be positive only. But in this, what is happening? Sometimes if you think of this as a railway track, okay, upon that wheel is there, sometimes torque is in positive direction, sometimes in negative direction, sometimes in positive direction, sometimes in negative direction, such that wear and tear will be tremendously high. Okay, so why this negative torque is coming? If you keenly observe, for example, here let me think of rotor induced voltage. Rotor induced voltage is this here. Okay, my rotor current should lag behind voltage or not? Yes, because rotor reactance is considered. So this is going to be rotor current lagging behind. Now this, let me divide it into two components. So this current is going to be in phase current IP. This current is going to be reactive component of current Ix. Okay. So about in phase component of current, whenever voltage and current are in line, already we have seen torque developed is going to be pulsational but unidirectional. right? So always it is positive or zero, but unidirectional, but pulsational torque. But here negative torque is also coming. Okay, so if I think of in-phase component of current, in-phase component of current is already analyzed when rotor resistance is considered by not considering rotor reactance. Now see here about Ix component, let me see. For example, this is going to be flux density in conductor X. So that flux density is this. This is going to be S omega S into T. Okay. Now what about the induced voltage? Induced voltage is same as flux density in line. Okay, induced voltage. Now let me think of current flowing because of Ix component, reactive component of current. Reactive component of current. Now reactive component of current should lag behind voltage by 90 degrees. Okay, so lag behind voltage by voltage in the sense red now, lag behind voltage by 90 degrees. So my current is going to be like this. Okay, now let us think of torque developed. Okay, so if I try to draw torque developed, okay, because of X component, reactive component of current, means B into I, black multiplied by blue. Black multiplied by blue in the sense positive multiplied by negative is going to be negative. Positive multiplied by positive is positive. So my torque is going to be, okay, so whatever the negative torque is happening, same positive torque will happen, same negative torque, same positive torque, such that T average created because of reactive component of current is going to be 0. Okay, so net torque is going to be 0. Net torque is going to be 0 because of reactive component of current. But oscillational torque will be there. Oscillation in the sense sometimes positive torque, sometimes negative torque, sometimes positive torque, sometimes negative torque, because of that huge wear and tear of the track will happen. Okay, so basically because of reactive component of current, oscillational torque is going to come or not? Yes. Okay, so reactive power, for example, if you think of inductance in our normal network theory way, what inductance will do? Inductance from the source, it will take the energy, store it, give it back. It will take the energy, store it, give it back. Okay, here also what is happening, sometimes it is taking the power from the source such that torque developed is one direction, and again the same power is being taken and supplied back to the source, torque will be in opposite. So power will be taken from the source, torque. Okay, power will be taken back, torque. So what is reactive power? Reactive power will produce oscillational torques. Oscillational torques. Okay, means oscillation torque, sometimes it will absorb power, at the same time at some other times it will deliver the same amount of power or energy to the source, such that oscillational torques will be produced because of reactive power. Okay, now coming to the point, let me conclude this. See, at starting I considered only rotor resistance by not considering reactance. When rotor reactance need not be considered, in our previous session with respect to slip, for example, this is rotor reactance. Okay, rotor reactance will reduce, and this is going to be 0 speed, and this is going to be ns speed, this is going to be rotor speed. Or else I can say this is going to be 0 slip, and this is going to be unity slip. Okay, now can I neglect rotor reactance in this area? No. Can I neglect rotor reactance in this area? Yes, because rotor reactance is less. Okay, so the moment rotor reactance is more, we have to analyze along with rotor reactance, like in our second case. Now, when rotor speed is nearer to synchronous speed, rotor reactance can be neglected. Rotor resistance only need to be considered. That is going to be this first case. Okay, so see here when rotor reactance need to be considered compulsorily, means that speed is nearer to 0. For example, in induction motor, I strongly hold the rotor not to rotate, then stator MMF is rotating. So in the rotor, I am going to get the twisting moment torque. Okay, so if I release that, rotor will accelerate from 0 RPM towards synchronous speed. Okay, so that is going to be starting time, transient time. Okay, so during transient of starting conditions, rotor reactance has to be considered. For example, once it reach running conditions, means that if synchronous speed is 1000 rpm, my rotor may rotate at 990, 930 or 950, something like that. So in running conditions, once my speed is achieved to stable speed, running condition is going to be steady state condition. Okay, so in running conditions I need not consider rotor reactance. So in the first case, whatever we analyzed with only by considering rotor resistance only, by not considering rotor reactance, means that this is running conditions. Running conditions means that low slip region, slip is going to be very less nearer to 0, or I can say low slip regions. Is it steady state or transient condition? Steady state. Okay, now let us think of starting conditions. Starting conditions in the sense rotor reactance also has to be considered. So in this case, this is going to be starting conditions. Okay, so in starting conditions, or I can say high slip region, because slip is nearer to 1. Is it steady state condition or transient condition? Transient condition, because rotor is achieving speed. Okay, now again let me conclude one more thing. Means very simple conclusion is, when rotor reactance has to be considered, when rotor reactance can be neglected. And second conclusion is about reactive power. Reactive power can be considered as torque developed with a net average torque of 0, but that is going to be oscillational torque, positive torque, negative torque, positive torque, negative torque. And third conclusion is, for example, forget about all. You know what is meant by electrical form of power. What is electrical power? Come back to here. Rotor voltage, okay, multiplied by rotor current, multiplied by cos of the angle between voltage and current. So VI cos pi is going to be active power, which is real power. Now VI sin pi is nothing but ER multiplied by IX is going to be reactive power, which is not a power. Okay, so if you apply this to here, whenever you have in phase component of current, it is actually producing torque or not? Yes, because torque multiplied by speed is power. Speed is constant because T average is speed will be decided by T average. So speed is constant, so torque variations are there, so power variations will be there. Okay, so means if you think of here, in phase component of current only will produce the torque. Okay, now means if I think of a triangle to voltage component of current Ix, which is reactive power, should not be producing any power at all. Okay, that's why what is torque developed, net average torque developed is going to be 0. So from electrical power point of view, voltage multiplied by current multiplied by cos of the angle between them is going to be active power, real power, is producing real torque. And voltage multiplied by current multiplied by sine of the angle between them is reactive power, which should not produce any power. Okay, it means it is nothing but a reactive power. So it is producing oscillational torque with net average of 0.